Welcome to another episode of learning. I thank each one of you for watching my videos and encouraging me. Please like my videos and share them with your friends and colleagues. Please join as a member and support my channel. Please subscribe my channel if you have not already subscribed. Thank you. We continue the discussion of the solutions of the problems from the question paper CSIR National Eligibility Test held in the month of March 2025. It is a rescheduled examination for Assam Center. In this video, we discuss the solution of a problem from the section Algebra, in particular from group theory. The given problem is on finite groups, and the problem is placed in part C, which is a multiple select question. There can be more than one answer, and it carries 4.75 marks. The question ID is 706563. This question is suitable for all these examinations. Right. The given question is, let G be a finite group. Right. For any prime number P, E of P is the set of all those elements G belongs to the group G such that G power P is equal to 1. G power P means G multiplied by G multiplied by G, P times is equal to 1. That is the identity element of G. Multiply means whatever operation is there, you do it. Compose. Which of the following statements are true? We are given 4 options. Option 1, if P divides order of G, then E of P is a subgroup of G. Option 2, for all P, E of P is a subgroup of G. Option 3, if E of P is a subgroup of G, then P divides order of G. Option 4, if G is abelian, then E of P is a subgroup of G. Let's now discuss the solution of the problem in detail. We have a finite group G. Further, it is given for any prime number P, we have E of P defined as the set of all those elements G belongs to the group G such that G power P is 1. We note that E of P is not empty. Why? E belongs to G satisfies this one. E power P, E multiplied by P times is equal to 1, the identity. So note that E of P is not empty because E belongs to, the identity element belongs to E of P. Right. We continue in the next slide. We take up option 4. If G is abelian, then E of P is a subgroup of G. Right. We believe that it is true. Right. Let G be an abelian group. Abelian group means it is a commutative group. That is, the operation that is present in G is commutative. That means AB is equal to BA for all AB belongs to G. Right. Is the question we are asking, is E of P a subgroup of G? So I want to prove E of P is a subgroup of G. Now, because G is a finite group, it is enough, it is sufficient to show that E of P is closed. There is no need of showing the inverse also belongs to that one. No, one condition is sufficient. Right. So, let A and B be any two elements of E of P. This means A power P is 1, B power P is 1. Now, where is AB the product? Now we test the condition. The product AB to the power of P is equal to A power P into B power P because G is abelian. When G is abelian, AB, the product to the power of N, is equal to A power N into B power N. This is a well-known fact. This is equal to A power P is 1, B power P is 1. Right. So, this means AB belongs to E of P. E of P. So, thus, the product AB belongs to E of P for all elements A comma B belongs to E of P. That is, E of P is closed. Therefore, E of P is a subgroup of G. So, this proves the option 4. Right. We move to the next slide for the discussion of the remaining options. Right. We go to option 1. If P divides order of G, then E of P is a subgroup of G. Okay? Okay. Now, just now we have seen whenever G is an abelian group, E of P is a subgroup of G. So therefore, what we do is we look for a group G which is not abelian and look at groups of order 2, 3, 4, 5, they are all abelian. The first non-abelian group is S3 whose order is 6. So we have seen that E of P is a subgroup of G whenever G is abelian. Therefore, we look for a non-abelian group and examine the option 1. Let G is equal to S3. It is a non-abelian group of the smallest order. Right. So, how G is equal to S3 will look like? It is a set of all permutations on the set 1, 2, 3. It consists of E, a transposition 1, 1, 2, 1, 3, 2, 3, a cycle of order 3, 1, 2, 3, cycle of order 3, 1, 3, 2. Right, this is S3. This is S3. Let P be 2. We take 2. Then 2 divides order of G, that is order of S3, that is 6. 2 divides 6, yes. 2 divides 6. Now look at E of 2. E of 2 is a set of all those elements G belongs to G such that G square is 1. Who will be the elements of E2? Certainly E will be there. And all transpositions when squared will be 1. When composed itself by once more 2 times, then it will be 1. So it is E 1 2 1 3 2 3. Right. 1 2 3 is not an element in this because when you square it, you will get 1 3 2, which is another cycle of order 3. You are not getting 1. Its order is not 2. Its order is 3. Therefore, these are the elements. Now the question, E of 2, is it a subgroup of G? If it is a subgroup of G, by Lagrange's theorem, its order, the order of E2, which is 4, must divide order of G, that is order of S3, that is 6. Is 4 divides 6? No. No. Therefore, it is not a subgroup. If E of 2 is a subgroup of S3, then by Lagrange's theorem, order of E of 2 is 4, divides order of S3 is equal to 6, and 4 divides 6 is not true. Therefore, E of 2 is not a subgroup of S3. So, here 2 divides order of S3, E of 2 is not a subgroup of G. So, option 1 is not true. Move to the option 2. For all primes P, E of P is a subgroup of G. No. For P is equal to 2 in this group, it is not a subgroup. We have seen. So, this is not true by the above example given in option 1. The same example. Right. Therefore, option 2 is not true. So far, option 4 is the only statement which is true. We move to the remaining one option. Option 3. If E of P is a subgroup of G, then P divides order of G. Okay. We take the group G is 1 omega omega square, which are the cube roots of unity, and it forms a Abelian group under multiplication. Right. And for any prime number P, E of P is a set of all those elements G belongs to, G power P is equal to 1 is a subgroup for any prime. For any prime is a subgroup of G, since G is Abelian, because 1 omega omega square is an Abelian group by option 4. So E of P is a subgroup. Right. Now I take P is equal to 2. Then E of P will have how many elements? 1 power P. 1 power P means 1 square is 1, correct? Omega square, is it 1? No. Omega square whole square. That is omega power 4. That is omega. Is it 1? No. So E of P will have only one element, and it is a subgroup of G. We have already seen for any prime number P, E of P is a subgroup. For P is equal to 2 also, E of P is a subgroup. But what is 2 prime? Does 2 divides order of G? No. What are you asking? Does 2 divide 3? No. Though, but P is equal to 2 does not divide order of G. So here E of P, E of 2 is a subgroup of G, but 2 doesn't divide order of G for this group G, that is 1 omega omega square under multiplication. So the option 3 is not true. Summarizing all the options, the answer to this question is option 4. And it is a good question, and I am sure that you have understood the solution of this problem. Thank you for watching my video. I thank each one of you for watching my videos and encouraging me. Please support me and my channel by joining as a member in the channel. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Yes, I am sure we are going to meet you all once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.